Okay, so we want to continue our discussion about lines, and the first thing we want to do is find yet another way of expressing a line. And it's going to be the following way. So maybe the title is going to be a line as an intersection of two planes. So if you think about it for a minute, if you take two planes, and suppose they're not parallel. If they're parallel, they're not going to intersect, right? But if they're not parallel, then they intersect, and their intersection, the points that are on both planes, form a line. Do you agree? Do you see that? Does everybody see that? Okay. So, for example, x minus y plus 3z minus 3 equals 0, and 3x plus 2y minus z plus 2 equals 0, this is a line. This is a system of two equations. Each of these two equations is the algebraic way of expressing a plane in three-dimensional space. Do you agree? Here, a is 1, b is -1, c is 3, and d is -3. Do you see equations of planes? Right? And the intersection of these two planes, the solutions to this system of equations, is a line. This is a line. Do you agree? Everybody? Okay. So okay, but we're not used to writing lines like this. We saw two different ways of writing lines. I left them here on the board. If you look here a second, we had the parametric form and the canonical form of the equations for a line. So that's what we want to do. We want to somehow convert that line, which is given as the intersection of two planes, and find it in terms of parametric or canonical form, or both. Okay? So how do we do it? So again, we're going to follow the same line of arguments, of thinking how to tackle problems of this sort. So look here, I'm here, hello. Thank you. So what do we have here? We have two planes that intersect, okay? And we want to find the equation of the line here in the intersection. How do we do it? So what do we need for a line? We need a point through which it goes, and we need the direction vector. Do you agree? So how do we find a point through which it goes? Any solution to this system, and usually there's going to be one, right? Because unless I really try hard to make two equations with no solution, usually there's going to be one, because right, there are three variables, only two equations. Usually there's going to be a solution, right? So any point that satisfies both is going to be a good point to take as the point through which the line goes. Do you agree? What's a bit more tricky to see, and by the way, geometrically, when is there not going to be a solution to the equations? When the planes are parallel, right? Okay. Now, and these are not parallel. How do I know? Just by looking at them, they're not parallel. How do I know? Right, their normals are not, what's the word? Collinear. The normals are not one a product of the other. Do you agree? So these are not parallel planes, hence there is a solution. So find any point that solves this, you're going to get a point. How do we find the direction vector? Okay, so the line we're looking for is both on this plane and simultaneously on this plane. Let's put this plane like this because it's a bit more stubborn. Okay, so it's on both planes. What does it mean that it's on this plane down here? It means, okay, it's on the plane, it means it's perpendicular to the normal to the plane. Do you agree? What does it mean that it's on the other plane? It means that it's perpendicular to the normal to the other plane as well. Do you agree? So a line which is on both planes, and it is on both planes, it's the intersection, it means it satisfies this and this. A line which is on both planes, the blue is the line we're looking for, the orange just fell, the blue is the line we're looking for, has to be simultaneously perpendicular to the normal to this plane, that's the red one, and perpendicular to the normal to this plane, that's the black one. Do you agree? Okay, so we're looking for a line that's perpendicular to two given vectors, the normals. How do we find a line perpendicular to these two vectors? Exactly. We take their cross product, we get a line perpendicular to both. Do you agree? So that's what I'm going to write now, and that's what we're going to do in this example after we pick up this orange. Okay, so in general, A, the direction vector, is going to be N1 cross N2, is a direction vector for the intersection line. Do you agree? Okay, and let's do it. Bless you. Let's do it for the example. So let's find the normals. So in our example, which is on the previous board, so I'm not going to go there, but you can take a peek over there. So N1 was 1, -1, 3. And N2, I'm just reading the normals off the equations of the two planes. That's very easy to do. We know how to do that. 3, 2, -1. Do you agree? Right? So what is A going to be? So therefore, A is going to be their cross product. And the way I calculate a cross product, when I know the components, is using this determinant business. Remember? So I write I, J, K, and then the components. 1, -1, 3, 3, 2, -1. And what do I get? In the I direction, I get 1 minus 6, -5. Do you agree? In the J direction, it starts with a negative before I calculate anything. And then I have -1 minus 9. So it's -10, but it's going to change into a plus 10 because of the minus that was there because of the J, right? And so let's erase this minus altogether. So -5, 10. And then in the K direction, I have 2 minus minus, so plus 3. So I get 5 again. So this is the direction vector. -5, 10, 5. Do you agree? Everybody good? Okay, so that's in our example. And now we need to find the point. Okay, so we have the direction vector. Now we need a point that satisfies the two planes. Okay, so let's go back to the two planes. Here they are waiting for us. And we want to solve this system of equations. How do you solve a system of equations? There are various ways. You're going to learn some sophisticated ways in your algebra course. But this is a very simple one. I'm guessing I can... Since I have 3 variables and only 2 equations which they have to satisfy, I'm going to have some degree of freedom. That's a professional term. Some degree of freedom here, so I can even try choosing z to be, let's say, 0 and then solving it for x and y. And it may not work, because maybe the line doesn't go through z equals 0, but I'll figure that out right away and try a different degree of freedom. Okay, so take z equals 0, for example. So we get the system of equations x minus y equals 3, and 3x plus 2y equals -2. Do you agree? And you know how to solve things like this, right? You put x equals 3 plus y, plug it in here, solve it for x, and then put it back to find y. Right? Everybody knows how to do that? So what you get, I'm just going to write the answer to save time. What I got is x equals 4 over 5 and y equals -11 over 5. Okay? So a point on the line is this solution, m0, which is 4 over 5, negative 11 over 5, and 0 for z. That's what I took. Clear? And if this was too fast, then read it slowly, and just to verify, take these three values, plug them into these two original equations, and see that they actually solve them. Okay? Good? Question?
Yeah.
Sure.
Is important if the lines is directed outside or inside the planes?
No, that's a good question. But that relates to the direction vector rather to the point. There's a lot of freedom here. We're making a lot of choices which are not important because the equation of a line, we didn't write it yet, but it's not unique. Okay? So for example, if I took these normals, if I called this one n2 and this one n1, then here I would have these two rows in the reverse order, and we already mentioned that the determinant would be minus this, right? And that's fine, because what we're looking for is the line, right? The line doesn't have a direction, okay? So the direction vector has a direction, but we don't care if it goes this way or this way, and we don't care about the magnitude of the vector. This vector would give the same line, for example, as negative 1, 2, 1. Do you agree? Everybody? Is it clear what I'm saying? Okay, so there's no uniqueness here, and in particular you can make many choices, and likewise when we found the point, what we found there, 4 over 5, negative 11 over 5, 0, you can choose z to be 17 and find a totally different point, and that's also fine. You'll get equations that look different. They may look very different, but they prescribe the same line. Okay, clear? There's no uniqueness. There's no uniqueness for equations of planes either. Okay? Okay, so let's just wrap up this business. So this is our A, this is our direction vector, and the point we found was 4 over 5, negative 11 over 5, 0. So conclusion, the equation of the line, maybe let's write it in canonical form, x minus 4 over 5, that's the x0, divided by negative 5 equals y minus minus, so plus 11 over 5 divided by 10 equals z minus 0, so it's going to be just z divided by 5. So this is the equation of the line in our example. Clear, everybody? Questions? Good? Hello, reply to this. No? Yes, good. Okay. Okay, good. So let's do some other similar sort of explorations. So how do we find a line through 2 points? This is a piece of cake. So you have 2 given points instead of 1, and you need a point and a vector. So you have 2 points, you need a point, you have it, right? Not a lot of work there. How do you find a vector, a direction vector? Just connect the 2 points, right? So if the 2 points are, for example, m0 is going to be x0, y0, z0, and m1, that's the other point, x1, y1, z1. So what's the equation of the line going to be? So A, the direction vector, is just going to be the vector connecting the points, x1 minus x0, y1 minus y0, z1 minus z0. Do you agree? Okay. So the equation of the line is going to be, now this might be confusing because there are x's, x0s, and x1s, and likewise for y's or for z's. So x is the variable. It's x minus, let's choose m0 for example, x minus x0 divided by L is x1 minus x0, equals y minus y0 divided by m is y1 minus y0, y1 minus y0, equals z minus z0 divided by n is z1 minus z0. So this is the equation. Clear? Providing these are not zero. Okay, do you see that? Do you agree? Okay, so maybe I'll take a color here, like blue, just to emphasize and write all of these in blue. Okay, so this is the general point. X, Y, and Z, and all the rest are given. Okay, all the rest are numbers in a concrete example. Clear? Good? Okay, good. Let's move on. How do we find the distance between a point and a line? So again, we're going to have to draw a drawing or wave our hands with some planes and lines and direction vectors and normals in them and try to figure this out. So the distance from a point to a line. So once again, we're assuming that the distance is to the closest point on that line. So we have a line. Here's a line. This is fun. We have a line and we have a point. The distance from the point to the line is not going to be the distance to here or to here, but rather the distance to the closest point on the line. That's going to be little d. Okay. Now, what is it in terms of the data? So here's the picture. We have this line here, and we have, so what do we know about the line? We know this given point M0, let's say, and we know the direction vector. Let's draw the direction vector on the line, starting here. So this is going to be A, the direction vector. And now we have a totally different point. Let's draw it somewhere here, M. And we want to know the distance from M to the line, which is the length of this thing. And this is perpendicular. This is the closest point. Okay? Do you agree? Now, if we knew what this point is, the closest point, then we'd be done, because we know how to find the distance between 2 points, right? We just take the length of the vector connecting them. Do you agree? But we don't know what this point is. Right? So we think, what do we know? We know the point M0, right? So we can connect these 2 points. Well, if we can do it, let's do it. So let's connect these 2 points, and let's call this vector M0M. Do you agree? Okay. And this is D. This is the distance that we're looking for. It's this thing. Right? It's not this thing. We don't want the length of this vector. This is precisely what we don't want. We want the nearest point. Now, does this remind you of something? What? I can't hear you.
Right triangle.
Right triangle is good. Okay. Take it a step further. Something that we've seen related to projection. Okay, you can see that this thing is the projection of this onto the line, right? Okay, in what context did this projection show up? The dot product. Okay, maybe that can lead us to a solution too, but I'm thinking of something else. Okay, maybe that would lead to a solution too. I'm thinking of something else. You have 2 vectors here. Okay, so here's a hint. Let's draw the parallelogram, which this distance word is in the way. Okay, now what does this remind you of? Cross product, good. So, and what is this D that we're looking for? It's the height of this parallelogram. Do you agree? So do you agree that D, well, do you agree first that the area of the parallelogram the area of the parallelogram equals D, the height, times the length of A. Do you agree to this? So do you agree that D, which is what we're looking for, is the area of the parallelogram divided by the length of A? And what is the area of the parallelogram? That's what you said earlier. Let's write it separately. So D equals, the area of the parallelogram is exactly the length of the cross product of the two vectors that the parallelogram is built upon. Okay? So this is precisely the length of M0M cross A divided by the length of A. Good? Okay? So if you see it without deriving it, it looks weird. Where did that come from? Okay? But that's what it is. Okay, so this is the formula for the distance between a point and a line. And note that all the data here is data that we know. So we know the length of A, because A is given, because we know the line. We know M0, it's a point on the line. Take any point on the line that you want. And we know M, that's the point that we're trying to find the distance from it to the line. Okay, good? So I won't do an example. You'll do some in tutorial or in homework, but it's just, plugging in stuff and doing the calculations. Okay, good? Okay, wonderful. Good. Okay, so more. What about various positions? This is getting to be a long one, isn't it? Okay, maybe let's stop here and just continue on the next clip. Okay.